Okay, folks, let's look at the page 407 assignment, okay? Okay, here we go.
Page 407. We're just going to do this whole thing on Desmos. Hopefully, you've already taken the time to go to Desmos and check your answers and figure out perhaps what you were doing wrong. I do expect these to be done on real graph paper. So let's go to Desmos here, and let's go full screen, make it easier. All right, first of all, not assigned, I have here the graph of tangent of x as a starting point. Remember how tangent of x works. Let's zoom in on it a bit here. All right, tangent goes through 0, 0. Tangent also, let's get some ink here. So tangent goes through 0, 0. Tangent, just like cotangent, has a period of 1 pi. Not a period of 2 pi, but a period of 1 pi. So it repeats itself every 1 pi. So starting here at 0, 0, you're going to go a half a pi here and a half a pi there for a total of 1 pi, and the whole curve fits in the space of 1 pi. From negative 1/2 to positive 1/2, the whole thing fits in there with asymptotes here and here. We can perhaps get a slightly better feel for the asymptotes by looking at where they head up here, and we see it getting closer and closer and closer and closer and closer to the asymptote, but it will never touch it. Same thing happens at each interval. We're getting closer and closer, but we never touch the asymptote. All right, let's go back where we were, back to the beginning, there. So it goes through 0, 0. If its period is pi, it must also go through pi 0 and 2 pi 0 and 3 pi 0, and over here, negative 1 pi 0. It also goes through 1/4 pi 1 and negative 1/4 pi negative 1. It leans to the right. All right. Now let's look at another one. Oh yes, this one, number 17. Number 17 was assigned. Let's see how this differs from 3 times the tangent. Notice the only difference is it's a whole lot steeper. Where it used to go through 1/4 pi 1, now it goes through 1/4 pi 3. Can we go up there and see that? There it is. 1/4 pi 3. Instead of the old 1/4 pi 1. So the whole thing just gets steeper. A little bit hard to graph that accurately, but I give you number 17 just to emphasize what happens when you take tangent and multiply by 3. It stretches it, makes the whole thing get steeper. All right, let's get rid of that. Anything else that you erase? No. All right, let's kill off that one. Now let's go to, that was number 17. Let's now go to number, what's next? Number 20, right? Yes, number 20 should be this one, I hope. All right, this one is negative 3 times the cotangent of x. Cotangent, remember, why am I not, oh, okay, this one is kind of tricky. Had me fooled there for a moment. Let's remove the negative 3 for a second. If I take out the negative 3, that's what cotangent looks like all by itself. Cotangent, remember, is the reciprocal of tangent. So for cotangent, what used to be a 0 becomes an asymptote. What used to be an asymptote becomes a 0. What used to be a 0 becomes an asymptote. And what used to be an asymptote becomes a 0. So the whole thing leans to the left instead of to the right. It doesn't go through 0, 0, but it goes through pi over 2, 0. It still goes through the same point here, pi over 4, 1. But the whole thing now, one cycle, is squeezed into the space of 1 pi. Again, from 0 to 1 pi, it squeezes into that space from 0 to pi because its period is pi. It simply leans the other way, goes through pi over 2 instead of through 0, and it still goes through 1/4 pi 1. Now what happens though when we put that negative 3 back in? First of all, let's see what happens when we put in the negative. If if I just put the negative back in there, it's going to take the whole thing and flip it this way, which is going to make it look exactly like tangent, except it's shoved over a half pi. But that wasn't the problem. This one says, how about -3 cotangent? -3 cotangent, let's just slip a 3 in there, and that makes it steeper. So it looks a lot like tangent, but it's steeper, it's shifted pi/2 to the right, and it's leaning to the right instead of to the left because it's -3 cotangent. Would I give you one like that on the test? No, probably not. It's just a little bit too ugly. All right, let's look at cotangent of pi/4. First of all, let's examine what's happening here. I hope you can see the yellow ink against the white background. We have an omega. Omega is pi/4. So we want to know what the period is. For tangent and for cotangent, we know the period is going to be 1 pi divided by omega. Well, in this case, we know that omega is pi/4 because we see it right there, pi/4. So to find out what the period is, we take pi divided by omega, pi divided by pi/4. You know how to divide by a fraction. We multiply by the reciprocal. So it turns into pi times 4/pi. Pi times 4/pi. The pi's cancel. We get a period of just plain 4. Not 4 pi, we get a period of just plain 4. Where is just plain 4? Just plain 4 would be a little bit past 3.14. A little past pi. We should have a period that's just a little bit more than 1 pi. Now, to find out exactly what that looks like, let's do this. Let's change our scale so that instead of, oops, got to switch tools here. Let's change our scale, so instead of counting by pi/2s, which I've been doing, let's change that to counting by 1s. This will make it easier to see. Now, we can see indeed that we have, and this is, oh, we haven't done, look, there we go. Oh, let's get rid of tangent up here. All right, there we go. Now, being cotangent means it has to lean the other way. It has a period, though, of 4, which means we're going to squeeze one complete cycle into the space from 0 to 4. And we can see it there. Let's back out some. We can see it better, perhaps. One complete period is squeezed in between 0 and 4. So we have asymptotes at 0 and 4 and 8 and 12 because the period is 4. And notice it's still halfway between the intercept and 0. It passes through 1. Halfway between the intercept and the asymptote, we have a value of 1. So that helps you get the right shape. Now, quick review here. Let's look at cosine. We know what cosine looks like. Cosine does not start at 0, 0. Cosine starts at 0, 1. Has that familiar sine shape to it. And we have one complete period in the space of 2 pi. Oh, look at this, 6. Guess what this value would be, right? Oops, I need some ink. Guess what this maximum value would be at right here. That would be at 6.2, 6.28, twice pi, 2 pi. But to make it a little bit simpler to view this, let's switch back to, I have to switch between tools here. Switch back to step pi/2. I like step pi/2 for these. So we're going to do step pi, where's my pi, divided by 2. So I change the step value to pi/2. That will make it easier to read. So now I can see I have my one complete cycle in the space of 2 pi. We have zeros at a half pi and 3/2 pi. All right, that's familiar to us. Why do we need that? Because what's secant do? Secant is the reciprocal of cosine. Secant being the reciprocal of cosine has this really cool familiar now shape that we like. It's going to do something like this, and this, and this, and this, and this, and this. Remember what this looks like now. What used to be a 0 becomes an asymptote. What used to be, there were no asymptotes. The maximum point becomes a local minimum. This minimum point becomes a local maximum. But the old zeros become the asymptotes. The old zeros become the asymptotes. The old zeros become the asymptotes. What happens though when we take that, and for this one we have not looked at yet, what if we multiply that by -4? It does two things. If we multiply by -4, it's going to stretch it, move it from, for instance, from 0, 1, it'll move it all the way up to 0, 4. But that nasty negative sign there is going to cause the whole thing to be flipped upside down. So instead of going up 4 and doing this, we're going to go down 4 and do that. So I'm going to go ahead and attempt to sketch this, then we'll ask Desmos how my sketch compares to the real thing. So instead of doing this, it's going to be flipped and moved up 4. It'll be like that. Here, it normally would do this, but because of the -4, it's going to be flipped and moved all the way down to 1, 2, 3, 4 down here like this. There. Let's do one more. Ordinarily, it would have been here, but that -4 says flip it and then move it up 4, so it'll be up here. Now, if I ask Desmos, and let's zoom, I can't zoom out. If I ask Desmos to show it to me, we have this. And there we have it. I see the blue, the blue, the blue. My graphs, my curves here are a little bit too blunt. They should have been sharper, I can see. So there it is. So I certainly had the right idea. I need to erase these. I have no big erase button. I've got to use my fist. Okay. Now, let's look at -3 secant of pi over 2. Why do they like these negatives? I'd like to see them give us a positive. -3 secant of pi over 2. Now remember, with secant, and just like cosine reciprocals, the period is 2 pi. So if the period is 2 pi, what's that tell us then? The period is going to be 2 pi divided by omega. In this case, omega is pi over 2. So we multiply by pi over 2, the pi's cancel, we get a period of 4. Oh, we saw that one earlier in a different context. We get a period of 4. To see that more clearly, I'm going to switch the step to step 1. There we go. I'm going to switch back to step 1 so we can more clearly see what's going to happen here. So we have a period of 4 with, what are we doing, this guy, and it should be upside down and 3. So we see a period of from 0 to 4. Between 0 and 4, we have one complete cycle. What does one complete cycle look like on this guy? It's a little weird. One complete cycle from 0 to 4 would be this, this, and this. From 0 to 4, it starts to repeat itself. And then again, it repeats itself. Might be a little bit easier to see if we looked at a complete period from asymptote to asymptote, from -1 to 3. Do you see how from -1 to 3 is also a period of 4? So between -1 and 3, what does it do? Well, we have this, oops, wait a minute, I just lost it. Oh, that's it, that's the whole thing. From -1 to 3, we have these two guys, that's one complete period. Then it repeats, then it repeats, then it repeats. And it's upside down, of course. Ordinarily, we would expect secant to be here, but it gets flipped upside down because it's negative. And we would expect it to start here, but it's moved down because the amplitude is 3. All right, erase these and move on. What else? That erase that little dot. I think I've erased it all. All right, let's go to the next guy, which is, I wanted to look at, this was not a sine, but I wanted to look at sine as a reminder. Let's get rid of cosine. Okay, there's sine. Very familiar, right? Oh, let's switch back to, depends on what the period of the next one is. Let's leave it as it is. We have a period of 2 pi. There it is, 6.28, right about there. Period of 2 pi. We have an amplitude of 1. It goes from +1 to -1. It passes through 0, 0, and it has this nice familiar shape. Notice that the 0 here is at pi 0, it says. 3.14, that's 1 pi. It's unfamiliar looking to us because we're counting by ones instead of counting by pies. But yes, 3.14 is pi. It's in the right place. Looks a little weird to us, but it's in the right place. Of course it is. This is Desmos. All right, so that's what sine looks like. Now, why do we care? Because cosecant is the reciprocal of sine. If cosecant is the reciprocal of sine, we would expect what used to be a 0 to become an asymptote. Cosecant would normally look like, cosecant would normally look like this, and this, and this, and this, and this. Cosecant's really pretty simple, but not quite the case this time because we have a different omega, a different period here. The period is going to be 2 pi divided by omega, but omega is, here it is 3 pi over 2. Did I say secant before? I was looking up here and thinking, this is cosecant. We're looking at cosecant. The reciprocal of sine is cosecant. I think I said that wrong earlier. So we're dealing with cosecant, 2 pi over our omega, which is a nasty 3 pi over 2, but that's not so nasty. You know how to deal with the fractions. That becomes 2 pi times, flip it, 2 over 3 pi. The pi's cancel. We end up with 4/3. We have a period of 4/3. Oh, gross. Period of 4/3 for this guy. Where's 4/3? That'd be 1 1/3. We need to have a period of 1 1/3, which will be someplace around here. That will be our new period. So this whole thing we have here is going to get scrunched. But not turned upside down for a change. That's nice. So all this is going to be scrunched so that this becomes here instead, and everything gets scrunched, and it's really, I'm sorry I gave this one to you. It's kind of nasty to try to graph. But let's see what it looks like when we punch the button here. Oops, I didn't punch the button. There we go. And I did a pretty bad job here of trying to show, oh yeah. It's not that one of these curves fits into the space of 4/3. It's one complete cycle fits into 4/3. So we have so here's 4/3. So in that space of 4/3, we have to have a complete cycle, which is this guy plus that guy. I was making it twice as wide as it should be. Yeah, pretty ugly, huh? Yeah. Hard to see it at first, but there we go. Let's move on. And the last one. 3 times the secant of 1/4 x plus 1. Okay, I'm not going to go through all the glorious details of this, except to mention, what does that plus 1 do? The plus 1 takes your whole graph and shoves it up 1 unit, making it especially ugly. Let's get rid of all this stuff. It also has a different period, so it's going to be kind of hard to compare it to, what's that? I have no idea what, oh. That came from, oh, that's what we're doing right now. I already tapped it. Yeah, we've got this omega value of 1/4. What happens when you take 2 pi and divide by omega, which is 1/4? That equals 8 pi. We have a period of 8 pi. We also have an amplitude of 3. So everything gets spread apart this way by 3 units up and 3 units down, and gets widened out to a period of 8 pi, which is why we have this curve way over here and that curve way up there. And to see this, we need to pull out some, and again, I've got the wrong tool. Pull out some, and out some, I said. There we go. And we can see it more clearly now. There it is. Notice the little wiggly sine curve here. And why are these things so huge compared to sine? Because again, we have a huge period, which makes it very wide, combined with a larger amplitude, which pulls it away from the axis, combined with adding 1, which is why it's closer to the axis here and farther away there, because it's been shifted up 1 unit. Yeah, on the test, I would not give you, these were especially nasty things to try to graph. I would not expect you to graph tough ones like this on the test. On the test, I would give you things that were much more straightforward. Yeah, much more straight. In fact, I'm not going to try to give any hints as to what I might do on the test. But if you can do these, if you can even come close with these, then you're in pretty good shape. If you understand the basics, then you're in great shape. All right, that ends that. Now, a little bit unusual. I have no new material for today. So there's only one video for today, and this is it. There's no new material because we are at the end of the chapter, believe it or not. So what I have for you, instead of new material, what I have for you is a review assignment. I sure hope you're watching this video, because if you don't watch the video, you won't know what the review assignment is. Okay, so the review is going to be broken into 2 parts. For today, due on Monday, will be part 1. So your test review part 1 is as follows. Let's see, where did I write that down? Here it is. Page 421, numbers 16 through 48 by 4, and 54, 57, 64, 66, 68, and 76. Okay, that is all due on Monday, of course, as always, by noon. All right, so there's part 1 on page 421. Okay, that's it for today. The next video that you see will not be new material. The next video you see will be the discussion of part 1 and the assignment of part 2. We'll talk about the test later. Goodbye.